in this video, let us learn about reverse biasing of PN junction diode. Now let us see what are the topics that we are going to discuss today. The topics are what is meant by biasing, the operation of the PN junction diode in reverse bias, how to plot the VA characteristics of the PN junction diode in reverse bias, and finally quiz. There is a quiz at the end of the video, so please do watch the video till the end. Now moving on to the topic, first let us see what is meant by biasing. So first let us define what is meant by biasing. Biasing usually refers to a fixed DC voltage or the current that is applied to a terminal of an electronic component such as a diode, transistor or vacuum tube in a circuit in order to establish proper operating conditions for the component. That means biasing refers to the fixed DC voltage or the current that is used to provide the proper operating conditions for the components. Now let us see what is meant by bias voltage. The bias voltage is the amount of the voltage that an electronic device needs in order to power on and to function it properly. So if you see here, this is the bias voltage which is plus 2 volts. And it is the amount of voltage that an electronic device needs in order to power on and to function it properly. Now let us see about the reverse biasing of the PN junction diode. In the reverse biasing of the PN junction diode, the positive terminal of the voltage potential is connected to the N-type semiconductor while the negative terminal is connected to the P-type semiconductor. So if you see here, this is a symbolic representation for the reverse biasing of the PN junction diode in which the positive terminal of the voltage potential is connected to the N-type semiconductor whereas the negative terminal of the voltage potential is connected to the P-type semiconductor. And this is the circuit diagram for the reverse biasing PN junction diode in which we can observe this is the DC biasing voltage in which the positive terminal of this voltage potential is connected to the N-type semiconductor whereas the negative terminal of the DC biasing voltage is connected to the P-type semiconductor. And to limit the current practically, a current limiting resistor is connected in series with the PN junction diode. So this is the current limiting resistor R which is connected in series with the PN junction diode and it is used for limiting the current flow across the circuit. Now let us see the operation of the PN junction diode in reverse bias condition. When the PN junction diode is in reverse bias, if the applied voltage is less than the barrier potential voltage, then there will be no conduction taking place between the P-type and the N-type semiconductors. So if you see here, this is the PN junction diode in reverse bias condition in which negative terminal of the battery is connected to the P-type semiconductor whereas the positive terminal of the battery is connected to the N-type semiconductor, and this is the current limiting resistor R which is used for limiting the amount of current flowing across the circuit. And we know that in the case of the P-type semiconductor, the holes are the majority charge carriers, whereas in the case of the N-type semiconductor, the free electrons are the majority charge carriers. Now if this applied voltage is less than that of the barrier potential voltage, then there will be no conduction taking place between the P-type and the N-type semiconductor. That's why there will be no amount of current flowing across the circuit. So the negative terminal attracts the holes in the P-type region away from the junction. Now this negative terminal of the battery attracts the holes which are the majority charge carriers in the P region away from the junction, whereas the positive terminal attracts the free electrons in the N region away from the junction. And now this positive terminal of the battery attracts the free electrons which are the majority charge carriers in the N-type semiconductor away from the junction. So hence no charge carriers are able to cross the junction. So due to this no charge carriers are able to cross the junction. So as the electrons and the holes moves away from the junction, the depletion region gets widened. So due to this, in the case of the reverse bias PN junction diode, the depletion region gets widened and this creates more positive ions on N-side region and more negative ions on P-side region. So if you observe here, these are the more negative ions on the P-side region whereas these are the more positive ions on the N-side region of the depletion region. So as the depletion region widens, the barrier potential across the junction also increases. So as the depletion region increases, the barrier potential across the junction also increases. Now the electrons in the P side and holes in the N side, which are the minority charge carriers, generate a small amount of current to flow through the diode. So now the electrons which are in the P side and the holes which are in the N side generates a small amount of current to flow across the PN junction diode. And this current is called as the reverse current, which is a combination of the electron current and the hole current. Now for a constant temperature, the reverse current is almost constant though the reverse voltage is increased. Hence it is called as the reverse saturation current and it is measured in milliamperes for germanium and nanoamperes for silicon. So the reverse biasing produces a voltage drop across the diode denoted as VR, which is almost equal to the applied reverse voltage. So finally the reverse biasing of the PN junction produces a voltage drop across the diode and it is denoted as VR. And this reverse voltage is almost equal to the applied voltage V. So this is how the PN junction diode is operated in the reverse bias condition. Now let us see how to draw the VA characteristics of the reverse bias PN junction diode. The response of the PN junction diode is indicated by its characteristics curve called as the VA characteristics curve, and it is a graph plotted between the voltage applied across the PN junction diode and the current flowing through the diode. Now from the figure, if the applied voltage to the diode is denoted as V while the voltage across the diode is denoted as VR, then the current flowing in the circuit is called as the reverse current and it is denoted as IR. So if you see here, this is the circuit for the PN junction diode in the reverse bias condition, in which the negative terminal of the battery is connected to the P-type semiconductor while the positive terminal of the battery is connected to the N-type semiconductor. So from the figure, if the applied voltage to the diode is denoted as V while the voltage across the diode, so this is the diode, and the voltage across this diode is denoted as VR, then the current flowing through the diode is called as the reverse current and it is denoted as IR. So if you see here, this is the direction of the reverse current flowing across the diode and it is denoted as IR. Now the plot of graph between the reverse voltage VR against the reverse current IR is called as the reverse characteristics of the PN junction diode. And basically the reverse bias characteristics can be divided into three regions. So if you see here, this is the representation of the characteristics curve for the PN junction diode in the reverse bias condition, which is plotted between the reverse current IR and the reverse voltage VR. Now the first region is the region from O to Q. As the reverse voltage VR is increased, the reverse saturation current IR initially increases. So if you see here, as the reverse voltage increases, the reverse current IR also initially increases. So this is the area at which we can observe the increase in the voltage and the current, and that is the region from O to Q. And this is the point which is called as the reverse saturation point and it is denoted as T. And this is I0 at which we get the maximum amount of reverse saturation current. The next region is region from Q to A. After a certain increase in the reverse voltage VR, the reverse current IR remains constant. So if you observe here, after a certain increase in the reverse voltage, the reverse current remains constant and this is the region from Q to A. This is the point A. And the third region is the region after point A. So at the point A, the breakdown occurs and the reverse current IR increases rapidly. So this is the point A at which the breakdown voltage occurs. And after this region, the reverse current IR increases rapidly. So the point A after which the reverse current starts increasing exponentially is also known as the knee voltage or the breakdown voltage of the PN junction diode. So this is the point A at which the breakdown takes place. And after this point, the reverse current starts increasing exponentially. So this point is known as the knee voltage or the breakdown voltage. The point to be noted is the reverse voltage VR applied to the PN junction diode is negative. So the reverse saturation current IR is also negative. So in the case of the reverse bias characteristics, the reverse voltage VR is negative and the reverse current IR is also negative. Hence the reverse bias characteristics are plotted in the third quadrant. So since both the voltage and the current are negative, the reverse bias characteristics are plotted in the third quadrant. So this is how the reverse bias characteristics of the PN junction diode are plotted. Now let us see the overall VI characteristics of the PN junction diode. So if you see here, this is the overall representation of the VI characteristics of the PN junction diode, in which this is the forward region characteristics curve and this is the reverse region characteristics curve. This is the point which is the cut-in voltage V gamma, and after this cut-in voltage the current increases exponentially. This is the point which is the reverse current leakage point, and this is the breakdown voltage or the knee voltage of the PN junction diode, and after this breakdown voltage the reverse current increases exponentially. So this is how we can plot the VI characteristics of the PN junction diode both in the forward and the reverse bias conditions. Now let us see some of the applications of the PN junction diode. PN junction diode can be used as a photodiode as the diode is sensitive to the light when the configuration of the diode is reverse biased. It can be used as a solar cell. When the diode is forward biased, it can be used in the light emitting diode lightning applications. And it is used as a rectifier in many electric circuits and as a voltage controlled oscillator in the varactors. So these are some of the important applications of the PN junction diode.